so we have our aldehyde here, and these these electrons here at the top are going to pull this positive Tollens reagent towards it, causing a positive charge to now be on the oxygen, straining it, and a water is going to come, and its lone pairs are going to attack this carbonyl carbon, forcing these electrons to go to the oxygen to stabilize the charge and have the water bond in place of the carbocation. And then this ammonia is going to come, since it has a lone pairs of electrons on the nitrogen, it's going to come and take one of the H's to stabilize the positive charge on the oxygen, leaving an OH. And Tollens reagent, since it's in a solution of it, is going to be readily available. So these lone pairs of electrons are going to pull this positive Tollens reagent towards this pair of electrons on this oxygen. And then the same thing is going to happen as before, where the oxygen now is going to have a positive charge, and the ammonia is going to pull off this H, taking these electrons, or taking this H and leaving the electrons on the oxygen. And now, the Tollens reagent is going to leave, but it's going to split the electrons that are bonded between the Tollens reagent and the oxygen, leaving one electron on the oxygen and leaving another electron on the Tollens reagent, forming an oxygen with 5 electrons around it. And this is going to pull the H that is on the carbon to bond to the oxygen, splitting this bond again, with one electron going to the H to stabilize and fill this octet up here, and the other electron being on the carbon. And as we continue, this lone electron is going to go to this oxygen after the Tollens reagent splits the bond again, taking one electron and leaving oxygen with the other electron, now causing this oxygen to have a negative charge. But this oxygen is going to form a double bond down here, taking one of the lone pairs of electrons formed from the hydroxide that was formed after it took the H, and have a positive charge. So now it's going to lose the hydrogen, forming a double bond, a carbonyl carbon double bond, and the H that popped off is going to bond to the negative oxygen.
So this is the mechanism for the iodoform test. So in this case, you have a ketone, or a carbonyl group. Any carbon next to a carbonyl group is called an alpha carbon. The hydrogens attached to alpha carbons are slightly acidic, which is why bases, in the case of this experiment, sodium hydroxide, its electrons attack to grab this hydrogen, which then breaks the bond and forms an enolate ion. An enolate ion is a carbonyl group with a negative carbon. So this enolate ion has resonance, which forms a double bond and then pushes the electrons up to form a negative oxygen. The enolate ion is what attacks the iodines, which then form this compound. From here, if in this case you have more than one hydrogen next to on the alpha carbon, the reaction will occur 2 more times for a total of 3 times to form a carbon with 3 iodines, which would cause for eventually to form iodoform, which is the yellow precipitate we'll end up for at the end of this part of the experiment. So after you reach this in the experiment, you have an alpha carbon with 3 iodines, and these make for a good leaving group. So in this case, these electrons will be pushed up to the oxygen, which will cause this carbon of the carbonyl group to be positive, which will then cause the hydroxyl group to attack it, which then the electrons from this oxygen will move down to form a pi bond, which will then kick off the C, which then from here, this will have 2 electrons, the carbon on 2 electrons, but will reach for the hydrogen, which the bond will break and push the electrons to the oxygen, which then you will end up with this and your iodoform compound.
For a ketone with a semi-carbazide. So first, this lone pair from the ketone will attack a hydrogen from the acid and form these 2 resonance contributors, and then the semi-carbazide will take these lone pairs and attack this carbon to form this, and then the water made from this previous step will attack one of the hydrogens on this positively charged nitrogen, pushing the electrons down to the nitrogen and forming a lone pair. And then this alcohol will grab a hydrogen from the newly made acid and form a positively charged oxygen here. And the electrons from this nitrogen will form a double bond and kick off the water and form an aminium ion. And then the water will take a lone pair and attack the hydrogen on the positively charged nitrogen, kicking down the electrons to this nitrogen and forming the final semi-carbazone. Okay, so this is the mechanism for a ketone with 2,4-dinitrophenyl hydrazide. So first, you take a lone pair from the ketone and attack a hydrogen from the acid, and you get these two resonance contributors. And then your 2,4-dinitrophenyl hydrazide will attack this carbon of this resonance contributor and form this molecule. And then this positively charged nitrogen will lose a hydrogen to this water molecule, and these electrons will be pushed down to this nitrogen and form this, and your alcohol group will take a hydrogen from the acid and form a positively charged oxygen here, and then the lone pair from this nitrogen will form a double bond, kick this water off and form this ion, and then your water will come take a hydrogen from the positively charged nitrogen and push the electrons down to form 2,4-dinitrophenyl hydrazone.